Okay, so in this video we're going to find three things. We've got to find a function for y with x. So y is dependent on x is our independent variable. We're going to find the eigenvalues when we've found this solution, and also the eigenfunctions. Now our function is this one here. Looks a little bit intimidating. We've got x squared times the second derivative of y, 3x times the first derivative of y, and we've got a lambda times the function of y equaling 0, and we've got these three conditions. So y of 1 equals 0, so when x is 1, y of x is 0, and when x is 2, y of x is also 0. And then the final condition here, lambda is greater than 1. So this lambda we know is a positive value and it's greater than 1. Okay, now looking at this, we've got a second derivative, a first derivative, and the function itself equaling 0. And we've got x squared, 3x and lambda, which looks a little bit like some sort of quadratic. We can see that this is an Euler Cauchy equation. So we need to treat this accordingly with these guides to see a solution for y of x. So as we've got x squared, a 3x and a lambda y of x, we can see that this will need some sort of a trial solution. So I'm going to say y of x equals x to the power of r being some sort of constant. Okay, now we've got a first derivative and second derivative of y with respect to x. So here we've got a y here, y of x. So if we take this first derivative and second derivative, and then we can plug that into here, see where that takes us. So dy dx, so the first derivative of this, obviously using the power rule, r comes to the front, the x stays, and then we reduce the power by 1. So that's our first derivative. And now we're going to need the second derivative as what we have here. We can put y of x here if you want, but I think you can see what I mean here. So now multiply r minus 1 and r together. So now we've got r minus 1, r, and then the x. And now reduce this by another one. So now we've got r minus 2. Okay, now we're ready to plug this into our equation here. So now we've got x squared. So let's start it over here, give ourselves a bit of space. X squared. Now the second derivative, so we've got r minus 1. So we've got r minus 1. I'm going to put the r in brackets as well. And then we've got x to the r, and then x to the minus 2. So we could break that apart if we wanted. So we could say x to the r and x to the minus 2. So the laws of indices, this is all valid. So I could put that in a bracket as well, so you can see what I'm trying to do. And then let's plug into this one. So plus 3x, and now the first derivative, which is r, which just again, I'm just going to plug that in inside a bracket. And then x to the r, again, as we did here, I'm going to separate these indices, and then x to the minus 1. And now we've got lambda times y. Now that's a little bit more straightforward. We've got our lambda, and the y is just x to the r. So nothing else to plug in there. So that's a 0. Okay, so now we've gone from this to this, which is looking even more messy. So we've got some tidying up to do, if possible. Now x squared, x to the minus 2. Basically what this x to the minus 2 is just 1 over x squared. So these two are going to cancel out. So that gives us a bit of a tidy up there. And then here we've got something similar going on. X to the minus 1 is just 1 over the x. So again, this 1 to the over x, or x to the minus 1, and this x will cancel out. This integer here will stay. So that x and that will cancel out. These will all stay, and it will stay equal to 0. So let's simplify that up a little bit. Just going to put my box on these now just to make things separate. So what we've got left, r minus 1 r, and then x to the r, which I'm not going to put in the bracket this time, it's just a term on its own, and then plus 3 r times x to the r. So I'm going to leave the r in the bracket and then x to the r on its own, and then they've got a lambda x to the r, and then that equals 0. Okay, now we can see we've got something going on here. We've got x to the r, x to the r, and x to the r. So we can divide all the terms by x to the r. So let's just do that. So now if you do that, this will cancel, this will cancel, this will cancel. 0 divided by x to the r. Again, that's going to disappear. So now we've got r minus 1 times r. I'll leave it like that. Plus 3r. No need to change that. That can stay as it is. And then plus lambda equals 0. Okay. Next obvious step is to try and multiply this out, and we'll look like we're going to head towards some sort of quadratic. So now we've got r squared minus r plus 3r plus lambda equals 0. So r squared minus r plus 3r plus lambda equals 0. Okay, r squared minus r plus 3r plus lambda equals 0. That's going to simplify massively to r squared plus 2r plus lambda equals 0. So that's our quadratic. So we've got r squared plus 2r plus some integer or coefficient or multiple, whatever we want. Some constant, sorry. So now let's try and solve for r. So I'm not really sure how we can factor this out for a quadratic, or how to do the quadratic formula. So I'm going to try and complete the square. So let's just concentrate on these two terms. So now we've got r plus 1 squared. So that's going to give us r squared plus 2r, but now we're going to gain a 1. So we now need to subtract 1, add the lambda, set it equal to 0. Now let's bring this onto the other side. So r plus 1 squared equals 1 minus lambda. Bring these across, that's what we'll get. Let's take the square root. So get rid of this r plus 1 squared. So now we're left with r plus 1 equals square root 1 minus lambda. But just be a little bit careful here. We've got plus or minus, because taking the square root could give us either. And now all that's left to do is to bring this 1, subtract 1 from both sides, and we've got r isolated. So now our r equals minus 1 plus or minus the square root 1 minus lambda. Okay, so that's our x to the r. That's what we've got so far. So let's just write in here r equals minus 1 plus or minus the square root 1 minus lambda. Okay, now we know that lambda is greater than 1. So this is then going to leave us with a negative inside the square root. So we need to do something with this to just try and make things a little bit easier to find our solutions for y of x. So I'm going to rub this off the board, and then we're going to go into this bit. Okay. Okay, so we've got our r, which is in this format, which gives us an imaginary number. So now we want to try and write this in the form of an imaginary number. So as we remember from Calculus 2 classes and Calculus 1 classes, complex numbers are in the form of z, our usual standard notation for a complex number, equals a plus bi, where I is square root of minus 1. So now what we could do is just multiply this by minus 1 and put an I in front, and then we turn it into the format of a complex number. So now we've got r equals minus 1 plus or minus I times the square root of lambda minus 1. So that then gives us our new value for our I, for our r, sorry. Minus 1 plus or minus I times the square root of lambda minus 1. Okay, now this gives us some good options here now. We can use two linearly independent functions using sine and cosine, using this value for our r, and with the a and the bi, so our a and our b will be this one. And let's see where that takes us using the boundary conditions. So y of x equals, now some constant. We'll use capital A, not to be confused with our lowercase a. This was just an example to show us the form of a complex number. So capital A times x to the power of lowercase a. So that's our value here. So that's our a. And then what we're going to use is we're going to use cosine times the natural log of x and our b value. And then we can add that to another linearly independent function, which is b times x to the power of a. This time we'll use sine and then the same input, log of x times b. Okay, now we've got some stuff we can put in there now. We know our value for a, so that's going to be our -1. And then our b is the square root of lambda -1. And we could be confident with that because we know this input in the square root is always going to be greater than 0 because our lambda is greater than 1. Okay, so let's go ahead and do that. So y of x equals, so we don't know what our constant for a is just yet, but we can do this. X to the power of a is x to the power of -1. Cosine of natural log of x, and then our b is this one here, square root of lambda -1 plus b, x to the -1 sine of the natural log of x, and b is also square root of lambda -1. Okay, that's what we've got so far. Right, okay, so what can we do now? So we can go ahead now and try one of our boundary conditions. So y of 1 equals 0. So wherever we see an x, we can substitute the value 1. So y of 1, so that's going to give us a, x to the power of -1. Now 1 to the power of -1 is just going to leave us with 1. So that's going to disappear. And now we're left with cosine, natural log of 1. So we know that's going to give us 0. But let's just go ahead and stick with it. We've got lambda -1 plus b. And same thing here. X is 1. So 1 to the power -1. This is going to disappear. And then we've got sine, natural log of 1 times square root of lambda -1. Okay. So now let's move on, simplify this off. Y of 1 equals, so a times cosine, now this is all going to be 0 now because natural log of 1 is 0. So cosine of 0 plus b, sine again all 0. Now we know the cosine of 0 is 1, so let's just try that. So a times 1 plus b, and our sine of 0 we know is 0. Okay, now when we get y of 1, we know that it equals 0. So this lot must all equal 0. So if this is 0, it's not going to tell us much about our b because b could be anything and it could be 0. So we don't know what b is yet. But for that to be 0, we know that this whole term is 0. So therefore this must be 0. So the only way we can get 0 on here is if a is also 0. So therefore our constant for a is 0. So our a is 0. So that takes care of that. Let's just rub this off the board and try now our y of 2. So I'm going to take it off to here and then plug in. Let's see what we get. Okay, so now we can advance on this. We've just checked this boundary condition. That one is taken care of. let's have a look at this one. So now we've got y of 2. Now, wherever we see an x, we're going to plug in a 2, and then we're going to set it to equal 0. But in the previous part, we solved that a is 0. So all of this term here is also going to be 0. So therefore we can ignore this now and go straight into this one. So now we've got b, x to the minus 1. So we've got 2 to the minus 1. And then we've got our sine function, which is natural log of 2, and then square root of lambda minus 1. Okay, and that is set to 0. Okay, 2 to the power of minus 1, we know that's just a reciprocal of 2, so we can just rewrite this a little bit to help us. So now we've got 1/2 of b sine of natural log of 2 times lambda minus 1, and that equals 0. Okay, now let's see what we can do here. Now the half and the b, that is going to disappear, because if we divide both sides by 1/2 times b and divide this side by 1/2 times b, we're just going to still end up with our 0 here and just a 1 here. So now we can advance on that, cross this out and say that sine of natural log of 2 square root of lambda minus 1 equals 0. Okay, now this is where we can start to find our first eigenvalues, because when sine of something equals 0 and we don't know what this lambda is, all we know it's greater than 1, we know there's going to be several solutions in here, because our sine curve follows this kind of value and it equals 0 at all these points. So there's infinite many points on there. So let's see if we can isolate our lambda and see where that takes us. Okay, so sine of something equals 0. So when is sine 0? So sine is 0 at n times pi intervals. So it's n times pi. So whenever pi is 0, sine is 0. Whenever it's n is 1, sine of 0, equals pi. When we got 2 pi, sine of 0 equals 2 pi. So this we know is valid. So let's just write this over here. Sine of 0 is at n pi. So let's just keep that to one side. So therefore, what we've got is log of 2, square root of lambda minus 1, that equals 0 at n pi. So log of 2 times square root of lambda minus 1 equals n pi. And then just a little note, n equals any of the natural numbers. Okay, let's just make that a little bit better. That's not a very good natural number looking n, is it? So, okay. So now let's try and solve for our lambda. So first of all, we could divide by the natural log of 2 to get that out of the way. So we've got square root of lambda minus 1 equals n pi over natural log of 2. Okay, now let's just make some more space on the board. Let's take these off and let's see where, let's give ourselves a bit more space to work in. Okay, let's go for that. Okay, so now we've got square root here and this term here. So now what we can do is we can just square this term. So lambda minus 1 equals n pi over natural log of 2 squared. So that's our lambda there as it is. So add 1 to both sides. Lambda equals 1 plus n pi over natural log of 2 squared. Now, as our n has several values, what we'll do now is give our lambda a subscript. So we'll call it subscript n. So lambda n, depending on which n we pick, equals 1 plus n pi over log of 2 squared. And then that will give us our first eigenvalue. So this is our eigenvalue. So let's just plug this in up here. Give ourselves a bit of space. So lambda n equals 1 plus n pi over natural log of 2 squared. That's our first part, that's our eigenvalue. Okay, so previously we had for our function or our solution for y of x, now we had a as 0, so if we remember we went straight into our b, which is our constant, x to the power of a, sine of natural log of x, and then multiply that by our b, which is this part here. Okay, now what we need to do is plug in our solution for our a and b, and then plug in our solution for our eigenvalue. So first of all, let's just plug in our a and our b. So y of x equals, that's capital B. So what we're interested in here is our lowercase, so the ones like we did for this value here for the r. So a was minus 1, so that was our a value. And then this was our b value. So sine of natural log of x, and then square root of lambda minus 1. Okay, now our eigenvalues here, this was our solution. So now, I'm now going to introduce the subscript n in there now, because now we're looking for our eigenfunctions. So our eigenfunctions, so hence more than 1. So our n, which is our natural numbers, so from 1 and above. So our b, for our constant, we can keep that for now. X to the minus 1, so I'll just put that over x. And then we've got sine of natural log of x. So all the different values of x we can plug in. And then this time we've got a square root. And then we've got our eigen value here. So 1 plus n pi over natural log of 2 squared. And then here we've got a 1. So that one is included here, but here we've got the minus 1. So we now need to put our minus 1. Okay, let's simplify this off. So yn of x is b over x sine, and then our natural log of x was going to stay. Now let's see if we can do something with this. 1 and minus 1, we can see straight away they cancel. And now square root and a squared term, we can just take the square root of this term and put that next to our natural log of x. So n pi over natural log of 2. And then close the bracket for our sine function. Now our b here is a constant, which we don't know. So we can plug in just a 1 for that, we can ignore that. So we just want a function here for our y of x. So now we've got y of x, nx equals 1 over x. So I'm going to rewrite that actually. I'm going to put the x on the bottom and write this function on the top. So x on the bottom, and then I've got sine of natural log of x, n pi over ln 2, and that is our input for our sine, all divided by x. And that's going to be our eigenfunctions for this equation here. So that completes where we got to today, finding our y of x, our eigenvalues, which are here, and our eigenfunctions, which are here. Okay.